Problem 14.55 involves a ring. It's rotating in a clockwise fashion with these three balls attached to it, A, B, and C. They're separated by 120 degrees from each other. The center mass of the ring in a system, therefore, is moving with a velocity v naught I. Since there are no external forces acting on this, or no external impulses or angular impulses, then we have conservation of linear momentum and conservation of angular momentum. The length of a single string L is 200 millimeters, which is 0.2 meters. The velocity of the center mass is v naught I, and v naught has a value of 0.4 meters per second. Speed of each ball relative to the center mass frame is going to be called u, and u has got a value of 0.8 meters per second. In the figure, the A value listed right here is 346 millimeters, which is 0.346 meters. We're given that all three masses are the same. After the ring breaks, object A travels in this direction, and object B travels in that direction, and object C travels horizontal or parallel to the x-axis. I'm going to put an origin O right here for reference purposes. We're going to look at the conservation of linear momentum, and what you have is the total mass of the system times the velocity of the center mass. That's your initial linear momentum, and the linear momentum afterwards is given by the three balls in their relative motion, which is m times v sub a times the j direction, m v sub b times the j direction. We know that v sub b is downward though, and then plus m v sub c in the I direction. This is the orientation at which the break takes place. It has to be, because for velocity c to be horizontal or parallel to the x-axis afterwards, and we'll show this a little bit later. All right. If we look at the I part of this motion, we got 3m v naught right there equal to m vc, and so you solve for vc and find that it's 3 v naught, which is 1.2 meters per second. If you look at the j part of the motion, then you got 0 on the left, and that's equal to mva plus mvb right there, and that gives you the relationship that va and vb are negatively related. Still unknown though. We have conservation of energy, so that's 1/2, and the way we write out the energy expression dealing with the center mass is it's 1/2 times the total mass of the system times the velocity of the center mass squared, plus then the energy you have within the system, and there's three of them. They're identical. Each one of them has a 1/2 mu squared for the kinetic energy with respect to the center mass, and there's three of them, so that's the total energy before the breakup, and the energy afterwards is given by this expression right here. Of course, all the m's cancel out, cross through there, and you're left with this expression. That's 3 v naught squared plus 3u squared equal to 2 va squared plus vc squared, and since we know what vc is, we can solve for va, because what we did is substitute in here too, by the way, that vb is the negative va, and that's why we ended up with 2 va squared right there. So you end up with va equal to 0.693 meters per second, which implies that vb is a negative 0.693 meters per second. I stored that in 1 on my calculator. The next thing we look at is conservation of angular momentum. The angular momentum can be written by that problem that I worked out in class. I don't remember the problem number, but it's r bar crossed into mv bar plus h sub g, which is the angular momentum about the center mass frame. Well, the r bar crossed into mv bar, the m is the 3m altogether, and that's 0 because the r bar is going to be, as we see in the figure, it's going to be measured from here out this direction. It's going to be anti-parallel to the velocity, so that cross product is going to deliver you a 0 value right there. Okay, and then you got plus your h sub z, and it's got to be equal to the sum of the momenta, angular momenta afterwards. Well, initially then you need your h sub g, which is just going to be m times l times u for one of the balls, and you got 3 of them, and since they're moving clockwise, it would be a negative for the, since k is out of the plane of the paper. And then afterwards, your angular momentum about 0.0. The velocity a has an angular momentum, and it's going to be the distance a times v sub a times m. It's a minus because it's clockwise, and v sub c and d also is clockwise, as you can see from here, because the motion about a about this origin is clockwise, the motion of c about that origin is also clockwise, and the motion of d about that origin is 0 because it has no moment arm with respect to that position. So, coming back down into our equation right here for angular momentum, we can solve for D and we get 0.2002 meters. Now, I wanted to show that rounded off to 4 significant figures here instead of 3 because there's a slight error in this problem. This is what I want you to note, that the distance D must be equal to L for C to be parallel to the X direction. And see the velocity triangle that I have right here, because at this particular orientation, let's say with the angle phi, your relative velocity is u, and it's perpendicular to this line right here. And then your center mass velocity is parallel to the x-axis, and so this right here has to be my v sub c then, is the sum of those two velocities. And just before the impact or the ring breaks up, this velocity vector right here has got to be horizontal or parallel to the x-axis just at the breakup. Otherwise, it wouldn't be parallel to the x-axis after breakup. So that means that this angle phi right here has got to go to 0. That means that you are, so the v sub c then to be parallel to v bar, phi must be 0. Therefore, D would be equal to L exactly. And L is 0.200 and not 0.2002. I think the difference in this problem is because when they give us the value for the A up here, up 346, that is probably a little bit inaccurate. It's probably good to 3 significant figures, but not to 4 or 5, and that's probably why you get a different L value or D value right here when you look at the 4 significant figure, when it should be exactly 0.200. This problem was also posted on the board outside the main office.